Yeah, good morning, everyone. Thank you, Milena. So first of all, I want to ask, who ever heard of the Steiner Tree Problem in this group? Well, quite a few. That's nice. Whoever has worked with wind farm planning or operating wind farms or something like this? One, two, maybe three. Yeah, okay. So there's definitely something you will learn hopefully today. And in the first session today, we had two talks about more like modeling and operating or optimizing the operation of energy networks. And I think the second block is more about like designing new energy infrastructure. All right, so what to expect or what you could hopefully take away today is what are steps in designing wind farms? What is the Steiner tree problem and what is quota constraint variant? What are the advantages of a specialized or problem-specific approach to these type of problems? And in the end, some outlook of what are open problems, what I am working on right now. Okay, let's go. So current trends in wind power. So first of all, onshore wind power is a very low-cost renewable electricity option. And you can see over the years, the onshore capacity has been growing a lot. But you can also see that it was like getting higher. So these ones are the new installed capacities or repurposed, no, repowered capacities. And you can see there's like some growth in this, then there's a drop again, then there's like Corona, there's the war in Russia, but it's still growing again. And then you see the goals for the Zubau, for the new installed capacity in this purple line. These are the targets the government has in Germany. And you can see, it's not quite reached in the recent years. And I have actually one today. So there's like this energy monitor from Zeit Online. It's a very nice, interesting tool about renewable energies. And what you can see here on the left, for example, is the wind power new installments. And you have a goal of 6 gigawatt for this year. And for this year, I mean, it's only a snapshot from today. It's quite not reached, right? So there is some need for accelerating this wind power expansion. But as many expansion plans, this involves a lot of decisions. And I will show you a few now. So first of all, we have to find suitable areas. We have to decide on onshore, offshore. Then, like for example, here we have an offshore region where you have the sea depth, I guess, where you can actually place the wind turbines. You have some other wind turbines already installed, which you also have to take account. Then you have a detailed wind analysis of this area. For example, these are wind roses you take into account. And these you can read that most of the wind is coming from this direction. So you always look where the wind is coming from, not where it's going to. Then you have the intensity of the wind, like the speed, like in meters per second. And then you have the probability in that type of scenario, right? So the larger the pieces are, the higher the probability or the higher the probability is that this wind scenario is actually in place. Then you have to take, when you're taking onshore into account, then you have distances to settlements or other wind farms and so on. And then there's the problem, or not the problem, but the task of acceptance of the population, right? And recent years has become a very political question too, in Germany especially. So there's always, you have to always take the population with you. Otherwise, they're going to sue, they're going to be much more bureaucracy about this and so on. And then you have designing the wind farm itself. So how many turbines do you need? Do you only have the cost versus revenue? So you want to maximize profits, or you have, for the government, for example, you have the expansion targets. So there's a little bit more than profit, right? So you cannot not only say, okay, this is profitable, but we actually need this expansion. Then where to place the turbines in this wind farm park, in this wind park? There you have the interference problem, which is how these turbines interfere with each other. Then, of course, there's a minimum distance between these turbines. You cannot build them like right next to each other because then they will crash. And then finally, how to route the cables to connect the wind turbines to the nearest power grid. And then finally, then you have to build it and operate it. This one, I definitely not going to talk about this. And these 2 points I will discuss a little bit in this talk. Okay, so in the wind farm design is usually a two-step approach. First, you decide where to place the turbines. So this is the wind farm layer problem. And then you have the wind farm cable routing. So where to route the cable, the power cables. And there's been recently a very good PhD thesis by Martina Fischetti, who gives a very good overview of how to model this in mathematical programming using heuristics, exact approaches, and so on. And there were some recent papers where there's an exact and very highly detailed approach to this problem, but they can only solve very small instances, which are not very useful in practice. Then a very recent paper discussed the same things, basically, on a very large size, but only solved them heuristically. They could improve some solutions, but there's no chance of saying how good the solution actually is, right? And then for regional planning, they have an exact approach in large size, but they don't include routing. So they only look in a region where to place the turbines to fulfill the expansion target. Again, expansion targets instead of only maximum profits. And then to increase the acceptance in the population, also other objectives than only costs are of interest, especially the visual impact of these wind turbines or the cables. So the goal is to choose a subset of potential wind turbines to fulfill an expansion target by minimizing costs and visual impact of the turbines and the cable routing. So this is the topic of the talk. So now let's come a little bit more into the modeling. So to be a little bit more specific. So what we have is we have a set of potential terminals in our area. Then we have a set of substations which are connected to the overlaying power grid. And then you want to then you have a set of connections you can choose from, and you might even have some intermediate nodes where you can split the cables, or you have to route around something, and so on. And then we want to find the cheapest connection to fulfill an expansion target. Here for this target, we need 4 wind turbines, and these one are the cheapest to connect. Okay, and to be a little bit more generic, we have a set of potential terminals, which are the potential turbines here in blue. Then we have a set of fixed terminals, which are the substations in red. Then we have a set of so-called Steiner nodes, which are the intermediate nodes, which we can use for routing the cables. Set of edges are the cables. And then we want to find a tree connecting all fixed terminals and a subset of potential terminals to fulfill the quota with minimal costs. So the quota is our expansion target. The fixed terminals are the substations. Potential terminals are the potential wind turbines. This problem we can call a Quota Steiner Tree Problem in graphs. So what is the Steiner Tree Problem? So the Steiner Tree Problem in graphs is a classical combinatorial optimization problem. It goes back even to the 7th century, when there was a very simple but not trivial problem of given 3 points in a plane, find the intermediate node such that the interconnecting distance is minimal. So this is the general Steiner tree problem without graphs. You can extend this to an arbitrary amount of points which you want to connect on a plane, which is called the Euclidean Steiner tree problem. And then for the Steiner tree problems in graph, you say, given an undirected graph G with edge cost C and terminals T as a subset of the nodes in the graph, find a tree, a subgraph that contains all terminals such that the costs are minimized. And this problem is in general NP hard. We have 2 special cases which are solvable into polynomial time, which is if you only have 2 terminals, then you basically want to find the shortest path between these 2 terminals in the graph. And when all nodes are terminals, then you have a minimum spanning tree. And then you have a number of variants of the SDP, the Euclidean Steiner tree problem, which I just mentioned, the node weighted, where you have not edge weights, but node weights, then the price collecting, where you have some revenues on the nodes and edge costs. and so on. And there are also some reviews by Ivana Ljubic and Daniel Rehfeld, who was a former colleague of ours, who's giving a talk tomorrow, I guess. He wrote a PhD thesis, a very good one, on Steiner tree problems, and was one of the main developer of Scip-Jack. And Scip-Jack is the worldwide fastest exact SCP solver. It's built on the open source server Scip, which you have used, I guess, in the last 10 days. It used a branch and cut approach to deal with the exponential number of constraints, which I will show you in a minute. You have to use, or you can use to solve this problem, the Steiner tree problem, exactly. And for this, we use the directed cut formulation, which I show you also in a minute. Okay, I mentioned here we use the directed cut formulation. Just a short reminder, what is the cut in graph theory? A cut is a partition of V of a graph G into two subsets S and T, disjoint subsets, right? So you have S and you have T, and no node of T is a node V and node S. And then the cut set of a cut C is the set of all edges which traversing these two subsets. And when you look at a directed graph, a little bit of notation, you have delta minus, which are the incoming arcs into a set T. So right, coming from S, so A in this direction would be B, C would be in this set. You can also say this for delta plus, which would be the other way around. But we only need this one for now. Okay, to the Quota Steiner tree problem again. Given a graph G, we have the substation, which we call fixed terminals, potential wind terminals. Terminals are wind turbines. Then we have costs and a quota profit for every wind turbine. The set of edges, costs, and the quota. Right, you can see this here. W is the weight or the cost of the wind turbine. 10 is the quota profit, and so on. And then you find, wait, sorry, I'm confused. So, okay. And then we can formulate the problem in given in an undirected graph, a set of fixed terminals, a set of potential terminals, edges with costs, potential terminals with cost and the quota profit. The goal is to find a Steiner tree that contains all fixed terminals, that the costs are minimized. This is the pure Steiner tree problem in graphs. And this is the extension. A given quota greater 0 has to be fulfilled, which is basically the sum of every potential terminal you use in your tree. And this would be a solution or the solution for a quota of 40. Okay, how do we formulate this as an integer program? First, we transform the original graph G into a directed graph and shift the costs of a vertex, this W, onto all incoming edges. This looks like this, right? So we have bidirected arcs in each direction. And then on the incoming edges of a potential terminal, we add the weight of the node of the potential terminal. And then we want to find a tree rooted at some fixed terminal R that minimizes the cost and fulfills the quota, right? So we want to have a tree rooted at R having downwards the directed arcs to connect all fixed terminals and the potential terminals we want to connect, what you want to use. Okay, how do we formalize this? Is that we minimize the cost. We have variables on the arcs, and then we have these Steiner cut-like constraints, which is basically what I just explained. For any set V in this graph, which does not contain the root, so the root is the S set, and this V is the T set from the cut, we want to have at least one incoming arc. And using this constraint, we can ensure that every fixed terminal, which is not the root, is connected, right? So there will always, doesn't matter how I choose the set W, if I have one incoming arc, then this node will be connected. that's a problem. We have to make sure that's for every set this is the case. And of course, these ones are exponentially many. For the potential terminals, we have a variable y, if we choose this to use in our quota or not. And then we have basically the same constraint, and this is only valid, or we only want to have to fulfill this if we actually choose the potential terminal. And then, of course, we have to choose at least a minimum amount of potential terminals to fulfill the quota. So what I said is that we have exponentially many constraints to the Steiner cut constraints. In Scip-Jack, there's a cut separation procedure to separate these constraints. It's one of the essential features, and it relies on a maximum flow algorithm because of the max flow and min cut algorithm. So if we find the maximum flow to each fixed terminal, and this is greater or equal to 1, then this constraint is not violated. So the problem now is that the binaries y prevent the direct usage of this algorithm. So what we did was not to adapt this very well-working algorithm, but to transform the problem. How do we do this? So this is our original graph with fixed terminals and potential terminals. These ones are the y variables. What we do now is that instead of using these blue nodes, we add fixed terminals, the red ones, extra to the graph, and connect them via arcs from the root node with 0 costs. And we connect them from the original potential terminals also with 0 costs. And then we say the solution is not now that we connect everything, so the other solution would be this one, right? So we have these blue nodes which are connected. But now we want to say, okay, either we connect these new fixed terminals from the root node, or we connect them from the original potential terminal. And then we say, okay, the quota only counts if we connect them via the original potential terminal. So this solution would be the same as this one. So now we can formulate the transformed version only by using Steiner tree problems, Steiner cut-like constraints for all fixed terminals, which are now the original ones, but also the newly introduced ones, the artificial ones, I would call them. And then a little bit more technical, but now we have to make sure that the amount of potential we waste, so the potential we connect directly from the root node, is limited by the amount what we can actually achieve in our graph minus what we need. And we showed that these formulations, this one and this one, are actually the same. Okay, so this is basically the math part. And then back to onshore wind farming. Again, we have a region, and we have potential wind turbines, these blue nodes. The red nodes are substations, and we want to find a subset to fulfill a given expansion target with minimum costs on regional level. And these green shaded, pixels are basically the scenicness, we call them, like the value of the beautifulness of an area. And then, of course, we ended up with like multiple trees because these substations are connected by 0 costs, that we have them basically aggregated as one substation because it doesn't matter where to connect to the power grid. And we tested this on multiple regions in Germany. In these so I said in the beginning, there's a lot of like technical details in wind farm planning. A lot of these technical details are in the analysis of where the positions are. So there's like minimum distance constraints are in there. There's some stochastic effects, which energy, which covers the energy yield, which also covers the wake effect. This is the interference between these turbines. And then we had also some smaller region, but with a high number of Steiner nodes. And then our objective is our multi-objective approach. It's very simple. I think Stephanie will talk a little bit more about multi-objective in the next talk. And we only use the weighted sum approach that we have, like, so we can keep the structure of the problem. And then we have a lot of instances. We have small, medium, and large instances. And the edges, which are basically the variables, go between 6,000 and 500,000. And for one region where we have a lot of Steiner nodes, we even have 1.3 million. We integrated this into Scip-Jack. We introduced the shortest path reduction and the shortest path heuristic into Scip-Jack for this type of problem. And then we verify against a flow-based MIP formulation, which we solved by Gurobi. For the results. So let me go this through one by one. You have these 5 settings, basically. The flow solved by a standard out-of-the-box solver, then the original formulation, the transformed one, the reduced one, and including a heuristic. And what you can see already for the small regions, so the flow is this one, which can solve every instance in an hour, but much slower than if we use the full setting we have, right? So it's 2 orders of magnitude, almost 1 or 2, yeah, 2. So this was a very good start. Then for the medium type instances, we can already see that for a time limit of 6 hours, the flow formulation reaches its limit. First, it cannot solve the instances because it runs into timeout, or it runs into memory out, into the memory limit. So it cannot even finish solving the process of the problem. And then for the large instances, you can actually see that the most improvement is made by or you can see this in all of them, by introducing reduction methods. And then only for some instances, actually hard to find a solution at all. Okay, so this is why I want to show you the advantages of a problem-specific solver. First, the problem-specific solver can use specific reduction techniques using the structure of the underlying graph. It's very hard to do for a general solver, which if it doesn't know the problem. Then you have a problem-related cut separation algorithm, depending also on the structure of the combinatorial problem. Then you can introduce primal heuristics, finding good solutions, and fast, which is also solvers like Gurobi also have problems with. And then you have an efficient usage of memory because you can construct the cutting planes on the fly and don't have to include them in the model in the beginning, where Gurobi, for example, has the problems if you introduce it as a flow-based formulation where you have to put everything in the beginning. Then finally, we compared our approach to, so we have this integrated approach to a sequential one. We used the results from a previous Germany-wide study of optimal location to reach a target for 2050. And then we looked at this for the selected region and compared the position assigned by that study with our integrated approach. So we say, okay, for the region, the study assigned so many gigawatts of wind energy, wind power in that area. Maybe you can improve this by fulfilling the same quota, but choose a different position for the tables. And we actually can. So when we only minimizing the cost in a sequential way, we have cost of 133. And if we minimize the integrated approach, then we have less cost. So I don't know, 20%, 10 to 20% less costs. And what's also interesting is that if we look at the visual impact of these chosen turbines, we also have the benefit of that we also have a much less impact on the landscape too. And if we do this for the when we only focusing on minimizing the landscape impact, the same story is the same. First, we reduce the scenicness or the impact on the landscape by a lot, and also minimizing or having also less cost in the result, which is a very nice result. So this shows very clearly that to approach the problem integrated, it's much more efficient than having a sequential approach. Okay, now I come to end of my talk. So what we have learned, hopefully, that we know a little bit more about designing wind farms. We know what the STP and the QSTP is. And I don't know, some of you might actually take the exam. So maybe think a little bit about how these problems relate to each other, how you can connect them or something like this. So this may be for those who want to take the exam. We showed that this approach is very efficient for large-scale onshore wind farm planning, and the integrated approach is vital to avoid excessive cost and landscape impact. So what is next? So in Steiner tree problems, I showed also this in the results, that the reduction methods are the most effective or one of the most important things in solving these SCP-related problems. And so we only use the shortest path heuristic, but there are also some other reductions in the other variants, and maybe one can translate them to the QSTP. This is something very interesting to go on. And then we want to extend this classic QSTP towards single wind farm planning by introducing interference constraints, right? So this problem is a very, I think, very famous picture of an offshore wind farm where the wind actually is coming from the direction that every turbine behind this turbine is affected by this turbine. So this one reduces the productivity of this wind farm by a lot. So, and then we have this interference constraint, which makes the problem much harder because now you have these binary products. And that's it. So